Today, I'd like to introduce an emerging and very exciting field at the intersection of information science and materials science, DNA information storage, with a particular focus on how silica particles can enable stable, addressable, and long-term molecular data storage. At CD Bioparticles, we develop functional silica materials, and this technology highlights how advanced particles can support next-generation data storage concepts. To understand why this approach is gaining so much attention, let's first look at the broader data storage challenge we're facing. Globally, data generation is growing at an unprecedented rate, reaching the zettabyte scale. However, conventional storage technologies such as hard drives, solid-state drives, and magnetic tape have clear limitations. They require continuous energy, occupy physical space, and most importantly, they have limited lifetimes, typically a few decades at best. This makes long-term data archiving increasingly expensive and unsustainable. These challenges have driven researchers to explore entirely new storage paradigms, including biological molecules like DNA. DNA is nature's original information storage system. Instead of using binary zeros and ones, DNA stores information using 4 nucleotides: adenine, cytosine, guanine, and thymine. Digital data can be mathematically encoded into sequences of these bases and then synthesized as physical DNA molecules. What makes DNA especially attractive is its extraordinary information density and its proven stability over extremely long timescales. But how does digital data actually move into and out of DNA? That brings us to the write, store, read cycle. The DNA storage workflow can be divided into 3 key steps. First, digital data is encoded and chemically synthesized as DNA. This is the write step. Second, the DNA is stored in a protected physical form. Finally, when data is needed, the DNA is sequenced and decoded back into digital information. This general concept has been demonstrated in several landmark studies, including work by Banal and colleagues. While the concept is powerful, it's important to look at both the strengths and current limitations of DNA storage. DNA storage offers several compelling advantages: unmatched data density, long-term stability, and no energy requirement during storage. However, there are also challenges. DNA can degrade under harsh conditions, and large DNA pools require reliable physical organization and indexing. These material-level challenges are where innovative carriers and protective matrices become critically important. This is exactly where silica materials enter the picture. Silica is an exceptionally attractive material for DNA storage applications. It is chemically inert, non-toxic, thermally stable, and compatible with a wide range of environments. Importantly, silica surfaces can be precisely engineered, making them ideal for encapsulating and protecting sensitive biomolecules like DNA. In many ways, silica encapsulation mimics natural fossilization processes that preserve biological information for thousands of years. This concept has already been validated in several influential research studies. Research has shown that DNA encapsulated within silica can be effectively protected from heat, moisture, UV radiation, and enzymatic degradation. Beyond protection, silica particles also allow DNA to be physically separated into discrete files and functionalized on the surface for identification. This combination of stability and addressability is essential for scalable DNA storage systems. Let's take a closer look at how DNA is encapsulated and labeled on silica particles. In a typical workflow, DNA is first encapsulated inside a silica shell. The particle surface is then chemically modified, often introducing amino groups that enable further functionalization. Using click chemistry, short DNA barcodes can be attached to the surface, allowing each silica particle to be uniquely addressed and retrieved without sequencing the entire DNA pool. In addition to chemical barcoding, optical features can further enhance the system. Fluorescent silica particles add an additional functional layer to DNA storage systems. They allow real-time visualization, quality control during encapsulation, and compatibility with flow cytometry or imaging-based sorting. Different fluorescent colors can also be used to multiplex or categorize data files, improving retrieval efficiency. At CD Bioparticles, we have developed a versatile silica particle platform that supports these requirements. Our silica particles cover a broad size range from nanometers to micrometers, with excellent uniformity and low polydispersity. They are stable in both aqueous and organic environments and feature hydroxylated surfaces that are ideal for chemical modification. These properties make them well suited as carriers and protective matrices for DNA information storage research. Building on this platform, we also offer multicolor fluorescent silica particles tailored for advanced applications. CD Bioparticles provides fluorescent silica particles in blue, green, red, and near-infrared emission ranges. A wide range of particle sizes allows researchers to optimize for storage density, handling, or sorting requirements. This flexibility enables both nanoscale DNA encapsulation and microscale file-level organization. These optical properties open the door to more sophisticated encoding strategies. Different fluorescence channels can be used to represent different data layers or file categories. For example, near-infrared particles offer low background interference, while visible fluorophores support standard imaging systems. By combining particle size, surface chemistry, and fluorescence, complex and addressable DNA storage architectures become possible. So where could this technology ultimately be applied? Silica-protected DNA storage has potential applications in long-term archival storage, cultural heritage preservation, secure offline data storage, and even space exploration. Its ability to maintain information integrity over extreme timescales makes it especially attractive for data that must be preserved far beyond the lifespan of conventional storage media. To conclude, I'd like to summarize how CD Bioparticles fits into this emerging field. In summary, DNA information storage represents a transformative approach to long-term data preservation. Silica particles play a critical role by providing protection, addressability, and functional flexibility. With our broad portfolio of uniform, functional, and fluorescent silica particles, CD Bioparticles is well positioned to support research and innovation in molecular data storage. We look forward to enabling the next generation of data storage technologies through advanced particle engineering. Thanks for watching.